So, oh, sorry. Let's do a nice green. And let's have a look at this. So let's go back here. So we're going to do circular motion notes. Two-dimensional motion. It's very important. A lot of things display circular motion. Moon going around the Earth, pretty circular. It's actually slightly elliptical. Tires going around a wheel. There's a ton of things. Some of the things about this are not so obvious, but we are going to use Newton's laws again. But now we're changing the application. We're talking about them in a circular context. So we just got to recognize when we use them and how we use them. But we're going to use Newton's laws. We're going to have one little additional thing, which is I'm going to be able to calculate the acceleration in a circular motion problem using a little equation we don't know yet. That's the one additional thing. So the big idea is, I've got a pen. Uniform circular motion, UCM. Uniform circular motion occurs when an object moves around a circle in a constant speed. So when you just spin something at a constant speed, it's uniform circular motion. We really like that because, not by happenstance, but it turns out that the mathematics that we develop for uniform circular motion is directly applicable to the mathematics we need for wave physics. And wave physics in physics 2 is everywhere. Light comes in waves, sound comes in waves, mechanical vibrations vibrate in waves. Just goes on and on. Somebody once told me that physics is waves, and it's a bit of an exaggeration, but it's not far off. So if the math we learn now is directly applicable to the math we'll need in physics 2, this becomes an important topic for us. So take it to heart. Newton's laws apply to objects that are moving with uniform circular motion because they're laws, they apply to objects. We're going to talk about ending circular motion. And there's a bit of a conceptual thing about if I'm going in a circle and suddenly I'm no longer going in a circle, what do I do next? We'll talk about that. And then we're going to talk about different examples. And these are like the take-home systems. We have so-called soap on a rope. We have conical pendulum. We have a flat auto racetrack. And we have a banked auto racetrack. So we'll do those examples, and then we'll say if an object changes speed while moving. So this is now kind of slightly different. This is non-uniform circular motion. And we'll say, what can we say about that then? And we'll get to that bit. It turns out it's just a little bit of vectors, and we're okay. This final bit, which is motion in accelerating frames, that's a little bit, what's the word I'm looking for? It's a little bit specialized, let's say. So, uniform circular motion. Look at this diagram at the top, and I'll draw it again down here. So you're going in a circle. And that means if I take a picture of you now, your velocity is in that direction. And if I take a picture of you then, your velocity is in that direction. Same speed. So my arrow is the same length. Agreed? Yep. Same length because it's same speed. That's my velocity vector. I'm just going around a circle. Have I changed my velocity vector between the final point, which is there, and the initial point is there? Are these the same velocity or are they different velocities? Let's vote on this. If you think they're the same V, press A. If you think different V, press B. Same, not save, same. Same. If you think these are the same velocity, press A. If you think they're different velocity, press B. Constant speed. Okay? So let's look. I'm going to give you a couple more seconds. I've got 19. Come on! Use your physics. fundamental physics thinking on this. Let you go for just a few seconds long. Stop on 35. Stop. Ooh. So what's the difference between a vector and a scalar?
Direction.
Well, that's just a word. So expand on that, please. Vector has direction and magnitude. And what does a scalar have?
Magnitude.
Only magnitude. So if I said to you, and which is a scalar, speed or velocity? Speed is a scalar. So these have the same speed, don't they? Because of the same magnitude. Velocity is a vector, which means I not only have to look at the magnitude, but I have to look at the direction. Do these have the same magnitude? Do they have the same direction? No. So there is a change in velocity. V final minus V initial will not be the same. It happens over a certain period of time. Agreed? This is T initial. This is T final. This is V final. This is V initial. Can you think back to Physics 1? This is Physics 1. Can you think back to the beginnings of Physics 1? And can you tell me what the average acceleration is in terms of velocity and time? What equation would you write down for that? It's going to be delta V over delta T, which equals, yes, V final minus V initial over T final minus T initial. So my next question is, so does this change represent an acceleration? Yeah, there's an acceleration there. Is acceleration a vector or a scalar? Vectors have magnitude and direction. Okay? Where do I draw my acceleration diagram acceleration vector on my diagram? It points towards the middle. There's my A. And it's going to be called an AC because it's centripetal acceleration. Now, think about it. If the AC had a component in the direction of this velocity, it's a good man. I was just given candy, though I will not remember who gave it to me. Thank you. It will not affect my grading. So, if I have an acceleration in that direction, and I have a velocity in that direction, if I have an acceleration in that direction and a velocity in that direction, what will happen to the speed of my object? It will speed up, won't it? The direction will change, but it will also go faster and faster and faster. Why? Because there is a component of that acceleration in line with the velocity, and Vf equals Vi plus At. So accelerations change your velocity unless they are orthogonal to your velocity. This acceleration has no component in line with the velocity, so it doesn't speed it up and it doesn't slow it down. Question or comment?
So, when a car speeds up,
When a car
speeds up going in a circle,
Yes.
what is that?
Oh, so it is going in a circle. So it does have a centripetal acceleration, this acceleration to the middle. It is also speeding up. So it has an acceleration in front. Two components which added together give me my true acceleration. And we'll get to that. That's actually the last bit we get to. That's good. Good. So there is an acceleration in uniform circular motion, and it points to the middle of the circle. Question or comment?
It's a redundant point, but when you're driving around a circle, you're accelerating all the time, but your speed is the same.
Yes, that's exactly right. And that can only happen when your acceleration is at 90 degrees to your velocity. Otherwise it won't happen. Yeah. So, okay, so let's formalize this a little bit. So let's come along and we'll get, want my eraser. Let's just erase this a little bit. And we just read what it says, and it says, okay, a body that moves in a circle has centripetal acceleration. How many people have heard of centripetal acceleration? How many people have heard of centrifugal acceleration? Yeah, they're not the same. And I'm going to talk very little about centrifugal acceleration. I don't like it. Okay? We fell out. Okay? So we talk about centripetal acceleration. I'll explain why when we get to it. So, body that moves in a circle has a centripetal acceleration. Centripetal acceleration is directed towards the center of the circle. Centripetal acceleration has a magnitude. I do not prove this. I have no idea actually where this comes from. I've never really thought about it, but though I will look it up this weekend. But the
I learned about this in my last science class.
I'm sorry?
I learned about this in my last science class.
Oh, good. Okay. So, there's the beginning velocity. There's the second velocity. The way I do subtraction is I take my final velocity and I add the negative of my initial velocity onto it. So that velocity is pointing up and to the right. The minus of it points down and to the left because we want to subtract, and subtraction is adding the negative of the second vector. And so my vector points towards the middle. So that's my justification of it pointing towards the middle. It points 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 towards the middle. It has a value that depends upon the velocity. We should really call this speed, shouldn't we? The speed squared. Language gets a bit loose here. For me, anyway. I'll sometimes call this the velocity, and I'll sometimes call this the speed. But really, I'm not talking about v that. I'm talking about the magnitude of that, which is the speed. Yeah? The magnitude of the velocity is the speed. Yeah? No direction. Over the radius. Ooh, that's interesting. It doesn't go linearly with speed, it goes to the square with speed. So it's kind of interesting. Don't worry where that comes from. Just know it. Okay? So what is the centripetal acceleration experienced by a 5 kilogram mass that moves at 12 meters per second around a circle of radius 4 meters? So here we go. Put your mass inside the little thing. Put your velocity. Well, I'm breaking my rules here. My velocity is going to be 12 meters per second. Clockwise or counterclockwise? We'll sort that out later. We're just going to have one for the minute. Radius is 4 meters. A centripetal is equal to v squared over r. So A centripetal is equal to 12 squared over 4. A centripetal is equal to 144 over 4. A centripetal is equal to, what's that, 36? 36. What's the units going to be? Yeah, it's just acceleration. There's nothing wacky because it's centripetal. And my A centripetal is going to be AC.
So you don't need to know what the mass is.
Mass is not involved in this. Now, to get that mass to that speed involved putting energy into the system, and the bigger the mass, the more energy you've got to put in. So it's not like it doesn't matter from a mechanics point of view, but it does not affect your centripetal acceleration. So it's basically like that. Sometimes people, including me, will talk about a centripetal force. Where there's an acceleration, there's a force, and where there's a force, there's an acceleration. Agreed? We drove that into our heads. So sometimes people will talk about a centripetal force. I kind of drew a line a few years ago and said I want to minimize talking about the centripetal force. And the reason is that it is not a thing in itself. You don't get a centripetal force because you go in a circle. You need a force to cause you to go in a circle. The moon does not go around the earth because it chooses to. It goes around the earth because of gravity. So saying that the centripetal force for the moon is gravity is kind of cheating. It's like, no, it's gravity that causes the circular motion. It's cause and effect. It's like you don't get vacation money because you go to Miami. There's nobody at the airport saying, on vacation, here's $1,000. If you want to go on vacation to Miami, you need $1,000. You got that by working. You call it your vacation money, but it's your work money that you're using for vacation. Because what tends to happen is when people first begin and they think about centripetal force, they add it to the other forces that are there. So I have a tension in my string and I have a centripetal force. Absolutely not. The tension in my string is causing the centripetal acceleration. The centripetal force is how much that I need, how much of that tension I need. So the gravity, the force of gravity pulling on the moon is causing the circular motion. I can calculate how much of that force of gravity is used for the centripetal motion. And I could call that my centripetal force. So centripetal force is a debt. So I'd rather not talk about it. Because you're going to say in the end, sum of the forces equals ma. And centripetal force is not typically one of those forces. It's a tension or a gravity or something like that. So I'm kind of forewarning you, because some of my diagrams may still have centripetal force in it, and I don't like to talk about it. The book, I'm sure, talks about centripetal force. So we say a block of mass m moves in a circle, moves in a circle of radius r with a tangential speed. So v, took a picture, that's what I saw. Which trace best represents the relationship between the block's centripetal acceleration, AC, and its tangential speed? What you do with this is you're going to write down the equation. AC is equal to v squared over r. You're going to look at your axes, AC and V. So I'm going to change colors here. I'm going to have, let's go to, this is important, let's go to red. AC is one column and V is the other column, not V squared. So what I can do is, if I'm stuck, I can do a little table. Whenever you do a little table, you say, oh, I wonder what AC is when V equals 0. Well, it's going to be 0 squared over r. Let's let r equal 1. Let equal 1, just to make the math easy. Why have a complicated number? So I'm going to say 0 squared over 1 is 0. Let's let v equals 1. 1 squared over 1 is 1. Let's let v equals 2. 2 squared over 1 is 4. Let's say 3. 3 squared over 1 is 9. 4. 4 squared over 1 is 16. 5. 5 squared over 1 is 25. If I plot that out as a graph, I'm going to see that it goes, this is my R, sorry, this is my V, and this is my AC, and it goes boom, boom, Boom. Doesn't it go like that? It goes 1 and 1, 2 and 4, 3 and 9. Yep. Which is which graph? E. Later on, I'd like you to be able to plot these graphs, even with when I don't give you numbers. You just got to imagine numbers and plot them, and I look at the ratio of your points. But for the while, we're just going to recognize the trace. The other way of doing this, which people sometimes get into, is they go, oh, there's one axis, and there's the other. Oh, look, I squared my v-axis. That looks like that.
Doesn't matter what we make ours like. It's
Doesn't matter, yeah.
same.
It's constant, yeah. But some people can do it by observation. And I'm fine with that. Just put down by observation. Other people need to do this trace, and I don't mind that at all. It's like the most common mistake is people look at the equation and they go, oh, AC is equal to V squared over R. Oh, yeah, there's that. It's linear. Because they're looking at what the equation is, and they're not looking at what this is. This is not V squared, this is V. So by using a different colored pen, I'm emphasizing V. Not V squared, V is. If I said to you, plot AC versus V squared, what would my trace look like? You'd go, oh, it's AC versus V squared. Oh, it's boom. Yeah? That's Y. And if it was V squared, that would be X. Now, R's not changing. So it's not inverse. R's not changing, yeah? So it's just that. So can you see that? So there's a little bit of skill to develop with these things. And this next one is another skill. So this is a ratio problem. There's a layout to these, and I want to teach you the layout. Block moves in a circle. It has a centripetal acceleration. So a centripetal equals 9 meters per second squared. So is it going in a circle? My AC is there. What is the centripetal acceleration of a new block if it has triple the mass, 4 times the radius, if it has triple the mass, 4 times the velocity of the old mass, and it follows a path that is twice the radius? So I'm going to do a bigger radius. Let's call this R old. Let's call this R new. Let's call this M old. Let's call this M new. Let's call this AC old. Let's call this AC new.
So then AC old is the 9 meters per second.
So, good point. The AC old is the 9 meters per second squared. So the first thing you do is you write down your relationship. AC is equal to V squared over R. Sorry, my phone is sending me messages.
You'll need to unlock your iPhone first.
I don't want to do anything. So here's what you do. You say AC new, that's what I want to find, over AC old, is equal to, well, it's going to be AC new over 9. That's an important step because people mess up on that step. Which is equal to V new squared over R new divided by V old squared over R old. Which equals, now here's the thing. Just look at these ratios. It has triple the mass. Is mass anywhere on my equation? So ignore it. It doesn't matter about that. 4 times the velocity. Is velocity in my equation? Yeah. I don't know what the velocity used to be, and I don't know what it is now, but I know it's 4 times bigger. So let's say the old velocity was 1. Yeah, sorry. Let's say the old velocity was 1, then the new velocity is 4. And don't forget we've got to square it. And then path that is twice the radius. I don't know what the old radius was. I don't know what the new radius is, but I know it's twice as big. So I'll put down 2 for the new and 1 for the old. And then divide them. So you see I have 4 squared over 2 all over 1. 16 over 2 is 8. Most common mistake is people will tell me AC new is 8 meters per second squared because they didn't write this front end down. AC new over 9 is equal to 8, if you like, over 1. Let's do 8 over 1. AC new is equal to 8 times 9, 8 over 1 times 9, which equals 72. 72 meters per second squared. Can you see how great this is? I don't need to know the old original numbers. I just need to be comfortable doing ratios. And I think engineers often, they double something, or they triple something, or they halve something. You don't need to go back to first principles to recalculate. You just look at the equation and go, well, I did this, and I did that, and I did the other. This is my new answer. It's very, very powerful. So for almost every equation, I can ask you a plug and chug. I can ask you a graphical. I can ask you a ratio problem. And I'm keen that every one of my exams will pretty well have at least one ratio, at least one graphical, and there's going to be more numerical numbers because we've got to learn to do the numerical stuff. But you're going to get, and sometimes more than one of each of these. So think of it in terms of content and think of it in terms of skills. It's really good. Questions on that? I got 5 minutes, so I'm going to go on for a little bit longer. So. I want to give you a heads up. Oh, I want to do a bit of conceptual stuff first. So you're on a roundabout. You're on a merry-go-round. Yeah, you're on one of those things that your kids get on, and you're spinning faster and faster and faster. They have one down by the Children's Museum that goes really fast. And your older brother just pushes you off. Do you go in that path? 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 You're going round. It's going round like that. Which path do you follow? Is it A, B, C, D, or E? Let's have a quick vote. I'm going to give you 30 seconds for a vote. A, B, C, D, or E.
You say it pushes you upwards.
He pushes you off. Not overwhelmingly. He just pushes you off. Good question. Not overwhelmingly. He pushes you off. If you like, you're tied by a piece of string and he cuts the piece of string. Good question. I'll give you a couple more seconds because it was a good question. So. Okay. What do we say? Ooh. So, first clue, my original diagram had the path marked. I didn't realize, so I kind of went over it as quickly as possible. If you noticed, I added the A and the C and the D and the E, and the path was already in there, yeah? So I got to change that diagram to make this. But most people said B, which is the correct answer. So what's going on here? Inertia. Inertia says you do what you're doing. And if you're doing that by going that way at that instant and there's no force acting on you, then you will keep on going in a straight line. So left to your own devices, you're going to go along that path. What's causing you to change your direction is this centripetal acceleration. So if I cut the string, which is giving you the force which causes the centripetal acceleration. If I cut the tension in that string, so there's nothing pulling you. If I turned gravity off, the moon would just go in a straight line away from us. And you would just simply follow this line. And what happens is, I mean, how many people have been kind of fallen off a merry-go-round? Yeah. And what happened is you looked at your brother laughing as you went. I mean, your perspective is, you started off right next to him, and then as time passed, he got further and further away from you. Boom, 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 boom. You ended up hitting the ground here. And so from your perspective, yeah, you moved radially away. But what happened was he pushed you off there, and you went in that direction. And just you kept looking at him. That's the problem. You just kept looking back at him saying, I don't believe you did that. But you went in a straight line, okay? So this says, uniform circular motion, centripetal acceleration must always point towards the center of the circle. Centripetal acceleration must provide a force. Must be provided by, I'm right, must be provided by a force such as tension of the string. If the string is broken, the centripetal acceleration is lost, so the object no longer goes in a circle. The object is in equilibrium and thus will continue in a straight line at constant speed. Given the situation, geometry, the straight tangent line is what you follow. I'm just going to talk about this. There are videos online for these examples. I'd like you to look at those videos before next class, because if you can get a feel for what I'm doing, it becomes much easier. In every case, we're going to draw a force diagram, and we're going to say it's centripetal acceleration. The sum of the forces equals ma, which equals mac, which equals mv squared over r. And the rest is just Newton's laws. That's the bit that's new. So this is just one step more involved.
Checking my sources. My web search term.
So look ahead. Just see if you can get a little bit of insight before next time. And I will see you guys next time.